first speaker, Tzu-Chieh Wei, who is currently an assistant professor in Xianyang Institute of Theoretical Physics. He got his PhD from University of Illinois at Urbana-Champaign in 2004. And before 2011, he found a job. He do 2 postdocs at Waterloo and UBC. So let's welcome Professor Wei.
Thank you very much for your introduction. So first, I'd like to thank the organizers, including Professor Yifeng Li and Jenny Hong, for inviting me here and for giving me an excuse to come back and visit my family. Okay, so I know that it's going to be a 3-hour lecture and divided into 3 parts, but I don't know whether I have enough materials. So I would describe details, and you can stop me anytime you like. So this is a title that I put on the schedule, and these are the references that I will talk about. But I am thinking that maybe in addition to describing my results, I would also describing other people's results. So the introduction that I would like to make is things that Professor Wayne already proposed a long time ago, is topological order. And so this is not a complete list of what we know about topological order, but let me just describe. So the topological order, the ground state degeneracy will depend on the topology. And so therefore they are degenerate ground state. These ground states cannot be detected or distinguished locally. You cannot just do measurement locally and you will know different states. That's not possible. And usually the excitation of these systems has some kind of analytic behavior. And maybe the more modern language is the long-range entanglement that Denton and Xiaogang proposed some time ago. So my focus would be using entanglement would be to characterize entanglement in these ground states and see how much we can do. This has been pioneered also Kitaev, Presskill, and Xiaogang and Levin. And they propose topological entanglement entropy that can be used to detect topological order. So maybe we can ask ourselves why we want to use entanglement. One thing using entanglement is good is because so far we don't have a consensus of what the order parameter for topological order. This is in contrast to the conventional Landau paradigm that you could find a local order parameter and there will be symmetry breaking and you can use to characterize and classify phases. So if we can have something that you don't need to really know the underlying mechanism, and let's just say we just compute entanglement, and if the entanglement is non-zero, then we know there's a topological order. Then this is a very good thing because it's somehow a dummies for topological order. So we don't need to do anything, we just need to compute this. If there's such thing exists, then this will be a wonderful tool. And for this, indeed, the topological entanglement entropy can be used for that purpose, and you only need to know the wave function. And you can detect whether the existence of topological order or not. But on the other hand, you only have one single number. Maybe there are different topological phases all share the same number. So then how are we going to characterize these different topological orders? Fortunately, if you use entanglement in a smart way, you can actually extract further information, such as modular S and T matrices, which I'm going to describe. So in some sense, there's a recipe that you can use to detect topological order, and once you detect it, you could also use it to extract further information to characterize these different topological phases. So that's the motivation why we're interested in entanglement. So here is the outline of these lectures. So today I'll probably cover torical in a detailed way and tell you how we calculate the ground state entanglement. And if I have time, I would probably also discuss if we deform the torical wave function. For example, if we apply the so-called string tension, we want to favor one particular spin. For example, we want to favor spin up. Then in a large string tension limit, the system will be polarized. So if you continue continuously from the torical to this polarized state, this means that there must be a transition somewhere. So the question that I like to address is, at least can we use entanglement that I would have introduced here to characterize or at least detect such transitions. And this third part is related to using entanglement in a smart way, meaning that you can actually use entanglement to find the so-called so you can actually use entanglement to find the set of state called minimally entangled state. Jimmy mentioned this earlier in the morning. And from there, you can actually extract modular matrices. And I have a request. Some request from the organizer want me to talk about AQLT state for quantum computation. So I will try to squeeze that, but this topic is very different from this here. Okay, so let me say again, please stop me anytime, any question. Okay, so let me begin by just describing to you what is a Kitaev torical. So imagine that we are on torus, and it's a periodic boundary condition on a square lattice, and on each edge there's a spin, what we call a qubit, because two-level system, and so there are 2 to the n square number of qubits. So on the edges, and to describe the torical, let me just write down the Hamiltonian. So the Hamiltonian consists of 2 parts. One is called a star operator, as indicated here. For each vertex S, there is an operator, which is constructed by a product of Pauli sigma X operator. And the other type of operator is called plaquette operator. So it's quite obvious. There's a plaquette. For each plaquette, there's an operator BP associated with that, which is a product of Pauli sigma Z operator. Okay. So the Hamiltonian is sum of all these operators. And you can easily verify that these 2 type of operators commute. Well, first of all, the same type of operator, they commute because they construct from the same Pauli matrices. But AS and BP, they also commute. Well, it's very easy to see because if they are far away, these operators act on different objects, so they commute. But if they overlap, for example, if there's a plaquette here, then you have 2 edges that overlap, and even though the Pauli matrix is anti-commute, the product of these operators, they commute. Okay. So this means that this Hamiltonian contains terms that are commuting, therefore you can diagonalize completely. So the spectrum will be characterized by the eigenvalues of these operators. And we're going to be interested in ground states most of the time. Any question? I know there are experts in the audience that know this very well, but I want to be pedagogical, and so for students, please ask questions. Okay, so let me illustrate some of the property of the topological order exhibit in this model. So first, these operators, they commute. So therefore, you can count the ground state degeneracy. The ground state was satisfied. Go back. So because it's ground state, so you want to satisfy each operator as eigenvalue plus 1. So therefore, you require that these operators act on the ground state, actually return to itself with plus 1 eigenvalue. In the quantum error correction, this is usually called stabilizer. So how many independent equations by these would actually tell you how many degenerate ground state you have? So for each equation, you would chop your Hilbert space by half because you only pick up the plus eigenvalue. So you just count how many constraints. And we know that these operators, they're almost independent except that when you multiply all the star operator, you multiply all of them, so each edge will be covered twice. So therefore, they become identity. And similarly for the pocket operator. We have 2 to the n squared qubit, but the constraint we have is -2. This means that there are 2 qubit degree of freedom left in the ground state. So just to compute the degeneracy, this is effective number of qubits, and it's 2. But if you also consider a surface with genus G, it's very easy to see this is the number of edges, so number of spin, so number of edges, and this is the constraint from the star operator, from the pocket operator, -2 because product multiply them become identity, and therefore you see that it's a 2G. So the number of degeneracy is actually 4 to the G. So this illustrates first the topology dependence of the ground space. Okay, so we can actually view the ground state degeneracy from the quantum information point of view because we can find the corresponding 2 qubit operator. So let me define these as follows. So imagine that I have, let me first describe the Z operator. So I consider a loop here. This is loop around of this torus, and the other direction labeled by CZ2 and CZ1. So consider the product of Pauli sigma Z operator on these 2 loops. I label by Z for the obvious reason you see, and also consider the product of sigma X operator on these CX2, which cut across these edges. So the product of sigma X, I label them as X2 here, and product along these line, I label as CX1. So you notice that the difference of labeling here is 1 and this is actually 2. You can show that these 4 operators, they commute with the blockhead operator and star operator. The reason is simple because for each star operator, if they overlap, they overlap always with even number. So you can check that the anti-commute for the X1, which is defined on this curve here, and the Z1 defined on this curve, they only overlap with one single edge. So that means that they anti-commute because they construct from the Pauli operator. And similarly for the X2 here and the Z2, they also anti-commute. But these other operator, they commute. So X1, X2 commute because they are constructed from the sigma X operator. And X1 and Z2, they commute because they don't have overlap So this defines actually the qubit, the 2 qubit. So therefore, we know the ground space is equivalent to 2 qubit. And perhaps this was asked someone in the audience that this could be used in quantum memory, because you could store 2 qubit in this ground space. And you can imagine if you have a higher genus, you can store more qubit. Okay, but you could also see that because they commute with the Hamiltonian, so their action on the ground space would remain in any of the ground state will remain in the ground space. It's very easy to see because they commute, so consider that the X acting using the commutation relation, this H acting on GS just pull out an energy, so this means that this is an energy with the same as ground state, so therefore it's a ground state. So in fact, these are a logical operator on the ground state, on the encoded 2 qubit. Okay, we can also study the excitations. The excitation can be created from ground state by applying, for example, here you apply a Z operator at this edge. It does not so it commute with the Plaquette operator, so it does nothing to the Plaquette operator. However, it anti-commute with the star operator here and there. So the eigenvalue of the star operator would change to -1, and this would also change to -1. If you apply again here, then the -1 will move to here. If you further apply Z along certain curve, then these excitation will be moved around. So this is usually called electric charge. You could also apply the X operator that would change the eigenvalues of the Plaquette operator. So we create the so-called magnetic charge. So in fact, there's also another charge which is a bound state of the electric and magnetic charge, and it's a fermion. So the type of excitation, including the ground state, the vacuum, and these 3 other excitations, they actually is related to the ground state degeneracy. Okay. So I described you that the torical on the torus have 4-4 degeneracy, but I'd like to construct the ground state wave function. So I'll show you one way to create the ground state wave function. So first we can start with configuration that all the spin are 0 on the edges. So 0 and 1 in my definition are the eigenstates of the Pauli sigma Z operator. So if we start with 0, then the Plaquette operator are satisfied because BP applying on all zeros is still +1. But how are we going to satisfy the AS operator? Apparently, the AS would flip spins. For example, if we start with 0, 0, and we apply the AS, which is product of sigma X would flip 0 to 1. So the 0, 0, 0 will be flipped to 1, 1, 1. So therefore, apparently, this configuration would not satisfy the S. But if we consider the action of S, all possible actions, this means that you consider all possible flipping of 0 to 1 or vice versa, and you just sum of all these possible configurations, then you will see that this actually satisfies all the AS, because it's actually a projection into the space that's stabilized by these AS operators. Okay. So this is one ground state because there are 4 of them. Well, there are infinite many of them, but I just describe one in particular basis. So a pictorial way of understanding this is that so I want to consider a group. I want to consider a group that is generated by all possible AS, and apply the group element to the 0 and make equal weight superposition of them. So here's one particular example. If this G is a product of A1 here, A2, A3, A4, and A5, that particular configuration can be indicated by these loops. The red dashed line crossing the edge indicating that this is 1. 1, 1, 1, 1, and also a 1, 1, 1, 1 loop. So this ground state I label by 0, 0 is equal to superposition of all possible loop configuration like this. And you can see, you can easily see that this ground state is an eigenstate of the logical Z1 and Z2 operator. And what about the other ground states? So we know it's effective 2 qubit. The reason I label it 0, 0 because it just is equivalent to a 2 qubit with 0, 0 state. In order to get the other 3 state, you just flip. You flip by applying effective Pauli X operator. And I have already shown you how you construct these Pauli X operator. So it's the X1 is product of X on these non-trivial cycle. The X2 is product of X on these non-trivial cycle. So so you can also see that the degenerate ground state cannot be distinguished locally because even though I just say my X curve only apply on these, but you can actually deform, for example, this CX2 curve to here. The difference is just a constructible loop. These constructible loop can be constructed by these AS operator. And they are stabilizers, so it does not change the code. So imagine that if we want to distinguish the 4 different ground states by just measuring a local region here, I can always deform my X1, X2 operator to be away from that region. So therefore, locally, the reduced state is the same for all ground states. So this illustrates one of the property of topological order that these degenerate ground states cannot be distinguished locally.
So can you define the charge operator for measuring the magnetic charge?
So you mean this bucket operator? So I'm only define the X operator here.
Right.
Yeah.
I mean,
so this, if you want, you can think of this as creating a magnetic charge at 2 pockets, and then you move around, and then bring them back and annihilate. Yeah. So if you want, you can think of these are the so-called string operator has a non-trivial magnetic flux.
right. I mean, globally, do I have an operator acting on G alpha beta to measure the magnetic charge of the state?
So if you can measure this operator, then you know whether it's actually the other way around. If you measure the Z operator, because this is defined as maybe I can write it here. So basically this is 0, 0, and 0, 0 are basically eigen state of this. But I also have 0, 1. This one is -1, 1, 0. And I also have so using the Z operator, you can distinguish not completely. You can only know that whether it's with plus eigenvalue or negative eigenvalue. Yeah. So actually, what you pointed out or what you just asked actually point to maybe this is not the best basis. The best basis, as I will show later, maybe not today, is actually you want to define the ground state and choose a basis which are eigen state of the this x2 operator and also simultaneously z1 operator. This would be the so-called minimally entangled state. I will just leave this for the later discussion.
Question.
Yes?
In your system, is there any translational invariance such that, actually I'm curious about why you have to define your red line in that particular space.
So
can you define other space?
So I can define here, I can define any loop that loop around this non-trivial cycle, because you can always deform. So you can always deform the X operator, for example. So this is the one that I use, but you can always deform this. And the difference is just many star operator. And these star operators, they act trivially on the ground state. So you can deform this. But you can also deform, if you want, you can add another loop and deform this. So basically you can move around. Yeah. And they do not need to connect this location. You can move around, so it's actually entering this and then coming back on this side. It's the topology that matters.
Can I see the algebra between X and Z again?
X and Z?
Yeah, the algebra relations.
Oh, you mean because it's just like Pauli operator. The X and Z would anti-commute.
And X1 squared is 0?
Yeah. No, X1 squared is identity because they are a product of Pauli matrices. Yeah. So just think of them as 2 qubits.
I have another question. So,
yes.
So you actually have a very big lattice.
Yeah.
But in the end, you only represent 2 qubits.
Yeah. So it's not very efficient in regards to quantum memory. Yeah.
Okay.
One way out is that you can puncture the lattice, then you're going to actually have equivalently it's higher genus, right? Okay. Yeah. Okay, so yeah, the one pictorial understanding that I just show you is that the ground state is equal weight superposition of these loop configuration. But what about the other? I mean, you will see what the other ground state means. For example, I apply this x2 operator. We call the x2 operator I applied here. I mean, I can apply to any non-trivial cycle parallel to this axis. What it does is to flip 0 to 1. So this is 0, so it will flip to 1, so I put a dash. This will flip to 1, and then this would flip 1 to 0, so my loop would be just like that. Okay? So this means that this particular ground state has configuration. It's a sum of all possible loop configuration where the loop has R number of winding number in this direction. You can imagine that you could also apply the x1 operator, which is in the vertical direction, then would create a loop in the other direction. Okay. So this is also something related, it's also a topological property. Okay, and yeah, as I already said here, so these are characterized by the Pauli Z operator. It's just like 2 qubits. So this system is pretty simple. You can just think of them as 2 qubits. Okay. So the question that I like to ask now is how much entanglement do these ground states possess? So to do that, I need to show you what I define by entanglement. So first, I will describe what is entanglement entropy. That's what people usually use. And the other I would introduce is the so-called geometric measure of entanglement that we developed. And the reason we're interested in this is because in terms of computation, for large systems, this may be more efficient. And it turns out that this can reproduce some of the property that the entanglement entropy has. Okay, so let me maybe define what entanglement